This video camera is part of a computerized vision system attempting to work like the human brain. That means processing millions of pieces of information in milliseconds. Sequential computers can't handle that kind of speed, so computer scientists here are developing computers that work more like the brain in parallel. Today we take a look at the cutting edge of the search for computer speed, parallel processing, on this edition of the Computer Chronicles.
The Computer Chronicles is made possible in part by a grant from AFIPS, the American Federation of Information Processing Societies. AFIPS, sponsors of OAC 86, the nation's leading conference on business technology. For conference information, call 800-OAC-1986. Exploring today's business solutions. Additional funding is provided by McGraw-Hill, publishers of Byte. Byte's detailed technical articles on new hardware, software, and languages cover the latest in microcomputer technology worldwide. Byte, the international standard.
Welcome to the Computer Chronicles. I'm Stewart Cheifet, and this is Gary Kildall. Gary, what I'm doing with my toy trains here is trying to understand parallel processing. You tell me if I have it right. In a sequential computer, basically, you've got one track, one engine, let's say, carrying one piece of information or one instruction. In a parallel system, we could have two or more tracks, two or more engines, each of them carrying some of that information down the line, and therefore we could get the job done in half the time. And the problem is, of course, making sure this train knows what that train is doing. Now, am I on the right track?
Well, I'd say it's a good model. Well, Stewart, the basic idea is to take a complicated task and break it into small, independent tasks that can be carried out at the same time. For example, if we had 1,000 people, we want to move down this one train track, we could take several trains and move them to their destination. Or we could take 10 different tracks with 10 different trains and get them all there at nearly the same time. The problem is to coordinate, of course, on this end. Now, for example, your personal computer that you have right now has got a lot of parallel processes going on in it. For example, you've got a microprocessor in the keyboard that's watching the keystrokes, microprocessor in the printer that's watching the platen movements and buffering and printing data, and then a central processing unit that's coordinating all these activities independently.
Well, today we're going to try to find out more about parallel processing and try to understand it. It's certainly a very important area of computer research right now. We'll meet some of the top researchers and scientists in the field across the country, and we'll actually show you a parallel processing computer so you can see for yourself how fast it really is. We're going to start with a background look at parallel architecture, and we'll try to help you understand why we really need it.
Towering over micros, minis, and mainframes are the supercomputers, machines that can match one fingerprint among millions, simulate the forms of life, and design the weapons of doom. This kind of computing power, combining tremendous speed with processing capacity, has been the exclusive province of machines costing tens of millions of dollars. But a widespread interest in parallel architecture may change that. Parallel processing, or the dividing up of computations between processors working in unison, can be accomplished in different ways. The data bus is the most common method, but is effective only for a limited number of processors. The distributed crossbar is another way to distribute processing, although the need to interconnect each processor puts a practical limit to this system as well. The ingenious butterfly switch network is one way to expand the crossbar, permitting up to 256 processors in all. But regardless of the method used, the multiprocessor super minis are giving new number crunching power to specialized users. In San Francisco, the University of California recently installed a parallel processing machine for molecular modeling studies. The 64-bit machine from Floating Point Systems is capable of 38 million floating point operations per second. The new machine can reduce a night's worth of calculations to a couple of hours. With the help of their new computer, the department produces some of the most remarkable graphics ever seen on a computer screen.
Joining us now in the studio is Dr. Howard Resnikoff, currently visiting scientist at MIT Center for Biological Information Processing, and Dr. Resnikoff also was co-founder of Thinking Machines Corporation. Also with us, Dr. Eugene Brooks, a physicist who was involved in parallel processing research at Caltech and who is now involved in the same area at Lawrence Livermore Labs. Gary?
Howard, what does biological information processing have to do with parallel processing?
That's a good question, Gary. Certainly the most proficient parallel information processors are biological organisms. Let me give you one typical example. If you're driving your car along the street and a child runs out in front, within a tenth of a second, you respond and have your foot aimed toward the brake. What went on in that brief period? Well, light hit your eye, it traveled up the optic nerve, your brain created a plan, compared the information with some stored knowledge, and sent signals to the motor system to move your muscles. Now, the neurons in your brain switch in a millisecond. You had only a tenth of a second in the entirety. So the program that does this is only 100 steps deep. There must be an enormous amount of parallel processing.
Absolutely. Now, at Lawrence Livermore Labs, there are everyday problems being solved there. How is parallelism applied there in the solution to problems?
Well, we apply parallelism at Livermore Labs to do two things. One is to reduce the cost of a problem, to reduce the cost of a simulation, rather. The idea is to apply several cheaper computers to a single simulation than to apply one more expensive computer. And the other is to reduce the time at which a physics simulation takes. In order to make progress using physics simulations, you have to get your answers back quickly enough that you don't forget what the problem was to start with.
What would be a typical physics problem that you might solve?
Well, there are many problems you might solve. There are weather simulations. There are simulations of the deformation of metals. There are a variety
Let's take weather simulation, for example. What's inherently parallel in something like that?
Well, in a weather simulation, you divide up the space, the physical space, which you're simulating, into a large number of zones, and the update of the physical characteristics of each zone may go on in parallel, subject to some information from the neighbors.
You could compute each one of these zones separately and in sequence, but in this way, using your parallelism, you can just do them all together.
Yes.
Eugene, what's the factor of speed we're talking about in doing a weather simulation with a cray or doing it with a parallel approach?
Well, the factor in speed that you get when you use parallel processing to solve a problem is very much in question, basically because you might see a large amount of parallelism in a weather simulation, many thousands or millions of points that could be updated in parallel, but the cost of organizing the computation tends to interfere with effectively using that many parallel processors on the problem. So there's some range of parallelism that you have to exploit in order to utilize a processor efficiently.
Howard, if we take a look at the problem, let's say biological simulation and so forth, are we going to see parallel processing applied to actually artificial intelligence, for example?
I think we've begun to see that already. The example that I gave of biological vision is, of course, very similar to the examples of machine vision. But you have to realize that the amount of computing resource that's required is much greater than any serial machine can provide today. In the biological example of the human eye, there are more than 2,500 megabits per second of data falling on the eye. No machine available today is able to deal with that.
Eugene, when you were at Caltech, you worked on one version of a parallel processing machine called the hypercube. Now tell us what the hypercube approach is.
Well, the hypercube approach was a message passing architecture where you utilized many CPUs that were connected to each other and effectively sent computer mail to one another in order to get the work done. The data of the algorithm had to be distributed amongst all the CPUs by the programmer.
Okay, and you talk about biological. How good is the brain, as an analogy to look at, as a biological example of how to develop a parallel machine?
That's a very complicated question. We know so little about the way the brain works. Some people think there may be as many as 10 to the 12th neurons. That's a very large number. Electronics is not going to build machines that complex. On the other hand, they're very slow units. They're extremely unreliable. There must be a great deal of redundancy. The more fundamental question of how to structure the programs, the algorithms, seems to me to be the place where most progress will be made. And I think there must be general principles that underlie both electronic and biological information.
Okay, gentlemen, we'll continue in just a moment. First of all, let's go take a look at a real parallel processing computer. We'll look at the Alexi, and Wendy Woods has that story from San Jose.
All computers will be parallel processors by the year 2000. That's the prediction of Alexei's president, whose firm makes the Alexei 6400. Capable of operating up to 12 simultaneous CPUs, the 6400 is lightning fast, processing at a fraction of the speed of conventional serial computers, which is why it has already been sold to 60 major customers.
For example, General Motors is using parallel processing to design car bodies and to design parts for its vehicles and do structural analysis on its vehicles. The semiconductor industry is using parallel processing to design chips for new computers. They can get the same calculation for probably 1/4 the price that they can using a single processor.
Parallel processors don't come cheap. The top-of-the-line 6400 costs nearly $3 million. But Alexei sees this technology coming down in price and size as the industry realizes its potential.
Personal computers that are used in business today will be parallel personal computers in 10, 15 years' time. It's the natural step to take. Once you accept that we are running out of performance in serial processors, then developments will be undertaken in parallel processors.
Alexei sold $22 million worth of hardware last year. Not bad for a company pioneering a new technology. And this year, the company not only expects to break even, but to make a profit over its initial investment, after which the sky seems to be the limit. For the Computer Chronicles, I'm Wendy Woods.
Joining us now in the studio is David Rogers, the Vice President for Engineering of Sequent Computer Systems of Portland, Oregon. And back again with us, Dr. Howard Resnikoff of MIT. And if you hear a huge roar in the background, that's David's Sequent computer over there, which we're going to get to in just a moment. Gary?
Howard, at the beginning we had 10 trains colliding at the train station. Here's an example of parallelism. How well does that really model parallelism?
Well, Gary, as you said, it's a good model, but it's not perfect. For instance, for database search, where one is seeking some particular string, that works fine. But for problems of the type that Eugene was mentioning, the processors have to communicate a bit. And in that case, the topology of the network becomes important.
Right.
Okay, David, there's some incredible things going on the screen on your computer now. Tell me about this demonstration you're going to show us on the Sequent.
I brought with me today an example of a computation which can be divided into parallel segments. The calculation is known as the Mandelbrot set. It's a set of numbers in the complex plane, and it's a good example of a problem which is suited for parallel processing because it can be divided up and run on multiple computers simultaneously. The computer will, in fact, divide up, as is being shown here on the screen, the problem into many tiny segments. The system that I brought with me today has a total of 12 computers, and so the segments will be processed 12 at a time until the result is completed.
Okay, so as I understand, we're going to take a look and solve this problem with one processor, and then 2, and then 12 at a time.
That's correct.
Okay.
Here you see one processor generating a segment of the image which will fill the entire rectangle. Then in a moment we'll add a second processor and you'll see that the rate of rectangle appearance is doubled. And then finally we will add all 12 of the processors and you'll see that the rectangles are going up.
Okay, so at the moment we're seeing a visualization really of the rate at which one processor is solving this problem.
This is actually the second, right?
Right, we're now up to 2.
Okay, we're now up to 2 processors at a time.
And now all 12 will be at work, and you see that the rate of execution is gone up linearly, which is one of the advantages of parallel processing. Generally, one wants to accomplish one of 2 results with parallel processing, either a decrease in runtime in order to get results more quickly, or an improvement in throughput. One is measured in results per unit time, and the other is measured in time to reach a single result.
David, we talked about the hypercube as one architecture a few minutes ago, and what is the architecture you have? Give us a little explanation of what these different architectures do.
Yes, the hypercube is an example of a connection machine, a network of computers talking to one another, not sharing the same memory. The machine that I brought with me, the Balance 8000, is an example of a closely coupled multiprocessor. All of the processors share access to the same data at every instant in time. One would use a connection machine for problems where the rate of communication among the processors is lower and the distribution of the data is higher. And conversely, with closely coupled machines, one works on problems where the intercommunication is more frequent and the volume of data is larger.
Now, if we apply this to, let's say, the personal computer industry to some extent, is there any application, let's say, of parallelism in personal computing you can think of?
The recently announced PCRT actually allows for parallel computation. The RISC technology machine can be doing engineering and scientific computations, and the PC-compatible engine can be doing more commercial-oriented applications
How about
like spreadsheets.
applications to, let's say, in graphics?
Well, as you probably know, many computers that we think of as single computers today actually consist of several microprocessors, each dedicated to a specific function. That kind of functional distribution has been employed for a long time.
Howard, we just saw 12 processors at work in David's Sequent machine. Now, you were involved some time ago with thinking machines, and they have a massive approach, don't they? Tell us about that machine.
Yes, the thinking machine's connection machine has 64,000 processors, each of which is a relatively simple one, however, and again, a hypercube interconnection network. And so for a machine like that, which operates in an SIMD control mode, which means that there's an orchestra conductor giving the same instruction to all of the processors, graphics problems, problems that are related to image processing, and a wide variety of others as well, can be treated in a way that's similar to what you see here, but on a much more massive scale.
David, what are the applications in which your Sequent machine is being used?
We fall into several categories, some which are runtime-oriented and some which are throughput-oriented. The runtime-oriented ones are, like the example I brought with me, graphical applications, simulation of physical systems, as Eugene Brooks talked about. The throughput-oriented ones tend to be transaction-oriented, those things where a large number of people want to have access to the same database.
Okay, gentlemen, thank you very much. That's an impressive demonstration. Now, one of the leading research centers in the country for parallel processing is Carnegie Mellon University in Pittsburgh. In just a moment, we're going to go to CMU and take a look at the WARP project, so stay with us. When Captain Kirk tells Scotty to set the engines at warp speed, you know what he means. He wants the Enterprise to go fast. So when computer scientists here at Carnegie Mellon University started up the WARP project, you know what they had in mind. They wanted computers that would go fast, and that meant parallel processing. The computer scientists here at CMU are trying to build a parallel machine that can provide the computer power needed for vision processing, essential to the future of robotics. Because vision processing is easily divided up into separate computations, it seemed ideal for parallel processing and the localized memory approach of the WARP machine. Vision processing requires tremendous speed just to do the filtering needed to eliminate erroneous images, such as shadows or debris. A vision processor must perform 20 calculations per pixel per second. With a typical matrix of 250,000 pixels, that means 5 million computations per second, far beyond the speed of today's sequential computers. Dr. H.T. Kung heads up CMU's Parallel Architecture Computer Project, and he says building the machine is the easy part.
The difficult thing is usually in parallel processing is that after hardware is built, we don't know how to use it. That's the biggest problem. We want to make sure that whatever piece of hardware we build, we have ways of using it.
So Dr. Kung's approach is to build a parallel machine with a very simple architecture.
We want people to be able to use a WARP machine in a programmable way, so that they can change their algorithms, they can change their computation models anytime, and we should be able to support it. Okay, so what we have is a very simple machine, sort of in the hardware level, but we build a lot of software on the top of it.
To be useful in vision processing, the WARP machine not only has to recognize what it sees, it has to first translate the distorted images from its lens into the normal linear aspect ratio. And that computation requires tremendous speed, since the image is constantly changing as the computer scans its environment. The usual method of attaining computer speed is the supercomputer approach used by Cray, but Dr. Kung says the parallel approach is superior.
This will be the basic difference between doing things very fast, but very sort of big physical hardware, and doing things very fast on a small piece of hardware. If you will be able to do things fast on a small piece of hardware, you will be able to find a lot of new uses of it. you'll be able to carry your processing to the place where it needs.
One of the next big steps for the WARP project will be the use of very large-scale integration, which will reduce the size of these processor boards to a mere 2 inches by 4 inches. With that level of integration, Dr. Kung says, it's only a matter of time before you find parallel processing in your microcomputer.
You'll probably have a very powerful vision processors attached to your microprocessor system. You can do many more interesting things than you can do now because you'll be able to see things now. Yes, I believe that. That's one of the big things parallelism will buy us, is that we can do things very fast in a much cheaper way.
Yeah, Stewart, it's applications like image processing that may help bring parallel processing to the forefront.
Gary, let me introduce the two new gentlemen who have joined us here. First of all, Craig Monday, who's a vice president and co-founder of Alliant Computer Systems in Massachusetts, and also with us is Jeffrey Keenan, senior analyst with the investment firm of Hambrick & Quist here in San Francisco.
Craig, we've talked about the hypercube and the sequent. What is your company's approach to parallel processing?
Our approach to parallel processing differs slightly from that of Sequent or the hypercube in that we wanted to produce a range of products that would be used in engineering computing roughly from the $100,000 to $1 million price range. And more importantly, our goal was to provide a form of transparent parallel processing whereby people with existing applications, typically coded in Fortran, would be able to take them from existing uniprocessor machines and make them run in our parallel processor machine without having to redevelop the application.
Isn't this kind of a difficult problem to take a Fortran program, for example, that isn't really built to say it wasn't built with the model of parallel processing in mind?
That's true. It's quite difficult. It required some state-of-the-art development both in compiler technology and the actual low-level machine architecture to produce hardware-based scheduling and synchronization mechanism that allows the granularity of parallel processing to be so small that we can actually find a great deal of parallelism even in a Fortran program.
If you take what would be a sample customer for a machine like this?
Customers that have purchased machines and are using them include many of the Fortune 500 type companies that have R&D labs, companies in the telephony industry, the aerospace industry, and they use it for a range of applications from finite element modeling to speech synthesis and analysis, ray tracing problems, example.
Jeffrey, we've heard about parallel processing for a long time now. Are we at the point where it's really a commercial product? I mean, do we have a market now and a lot of people really selling machines that do this?
Well, I think really the 1985, 1986 timeframe is when we're going to first see some commercial successes in this market. It has been very long on promises and a lot of vendors attempting to get in at this point.
Craig, Gary mentioned at the very beginning of the show, in fact, even a personal computer to some degree has some parallelism in there. In terms of that level and people who watch our program, for example, what are the consequences to a computer user of the parallel processing technology which is taking place now?
I actually believe that one of the consequences is that technical computing especially is becoming bimodally distributed. Technical problems tend to now be solved where the problem is formulated and perhaps the input and output are done in the personal computer or workstation environment. And through the use of networking, parallel machines with much higher performance are being used in a server role to provide high-performance computation that's very tightly integrated into the environment of the personal computer user or the workstation user.
All right, we're going to have to change our way of thinking about the way we program to use the machines effectively.
I think it depends on what class of machine you're going to try and use. To use a hypercube, for example, I think it's going to require either new programming languages or at least new programming techniques. As I said before, the goal Alliant had was to be able to get reasonable efficiency as you added numbers of processors, even for languages like Fortran that were traditionally only used in scalar processing. So I think both will happen.
Jeffrey, talking about competition, we've heard a lot about the Japanese work in parallel processing. How does the effort of American companies compare with what's going on in Japan?
Well, in this particular market, the market Craig refers to, the gap filler, really it's the American companies taking the lead. The bulk of the Japanese effort is truly at the high end in the area currently served by Cray Research and Control Data.
Now, is this another area, I get the feeling, where the hardware is quite a bit ahead of the software and really the work that has to be done is to find more ways to use the technology?
I think that the significant progress has been made lately in both areas. both in the development of new languages and also in the development of improved compiler technology that will allow parallelism to be found at a low level and mapped into machines that have been very carefully designed to support that.
Also, it looks like the emphasis really is on scientific world to some extent. Is that true, or do we see business applications coming up for parallel processing?
I think there will be business applications. Personally, I believe especially in the database management arena. There's a great deal of potential parallelism to be had there. I think the companies, for example, like ours and Sequent and other startup enterprises have been driven into the high-performance engineering and scientific computing market, partly just due to market conditions and the presence of the major players in the data processing arena, and partly because the technology is very applicable or more readily applicable to a broad array of engineering problems.
Gentlemen, we're out of time. We need parallel television, Gary. Okay, thank you very much for being with us. I'll be back in just a minute with this week's Computer News. In the Random Access file this week, U.S. and Soviet scientists have reached tentative agreement on a new computer network that will link the Soviet Institute for Automated Systems in Moscow with the New Jersey Institute for Technology. The new computer network will allow Soviet and American scientists to share databases and work together on a variety of research projects. IBM says its recent price cuts and a soft market for capital spending will put pressure on IBM's earnings for the first quarter of 1986. The IBM statement suggested that the long-awaited computer turnaround is not quite here yet. They're still celebrating its zenith in the wake of the IRS decision to buy $28 million worth of the Zenith Z171 lap portable. And the IRS decision is causing some aftershocks. Analysts say the decision to go with a 5¼ disk drive machine will help the larger format stay ahead of the 3½-inch microfloppies. In addition to the Zenith hardware deal, the IRS also selected software packages to go along with the machines. They were Poly Windows as the desk accessory, Enable as the integrated package, and RBase 5000 as the database. In our legislative update file, the Senate Governmental Affairs Committee has released a report criticizing U.S. government computer security practices. The report says there is inadequate screening of computer personnel and lack of planning in the area of computer security risk analysis. A national report by the National Science Board says American high-tech research is basically in good shape. The report, though, warned of an increasing military role in research and a decline in the overall role of the federal government as a funder of R&D. The report said the biggest weakness right now is math and science teaching at the high school level. In Michigan, the influence of automation in the automobile industry is changing high school curricula. One high school in Grand Rapids is now teaching the 4 R's, reading, writing, arithmetic, and robotics. East Kentwood High has bought 6 industrial robots to start up its new program. Finally, a programmer in Iowa has come out with something called Babel 123. It's a speech synthesis program that's designed to talk in a calming and loving way to hogs. Swine researchers say hogs eat more and get fatter faster when they're happy. And research suggests that being talked to gently makes them happy. Babel 123 is being tested this month in Fairfield, Iowa. That's it for this week's Chronicles. We'll see you next time.
The Computer Chronicles is made possible in part by a grant from AFIPS, the American Federation of Information Processing Societies. AFIPS, sponsors of OAC 86, the nation's leading conference on business technology. For conference information, call 800-OAC-1986. Exploring today's business solutions. Additional funding is provided by McGraw-Hill, publishers of Byte. Byte's detailed technical articles on new hardware, software, and languages cover the latest in microcomputer technology worldwide. Byte, the international standard.